Hello, folks. I'm going to talk through the lesson for the second half of this week's module, which is on sampling and sampling distribution. So you should have read the 10 pages from the Healy textbook in preparation for watching this lesson. There's really two parts to this lesson. The first one is on sampling and how do we get good samples and different types of samples. And then the second part of the lesson is some kind of conceptual rules of statistics when it comes to what are called sampling distribution. So good news is that there's no real math involved in this, that this lesson is all just conceptual. Okay, some language to get through first. So much of what inferential statistics are about involve what are called estimation procedures. And estimation procedures use sample statistics to draw conclusions about population parameters. Heads up that anytime we're talking about a characteristic or variables of a sample, we call those statistics, right? So anytime we're saying something about a sample, those numbers are statistics. Anytime we're talking about characteristics of a population, numbers related to a population, those are called parameters. So just some important lingo to distinguish: for statistics is about a sample, parameters is about a population. So the first type of sample we'll talk about is what's called a probability or random sample. Don't think of random as haphazard or unplanned, but rather a random sample in the context of statistics is very well planned, very intentional, right? So a random sample is one in which that has two characteristics. The first is that it's representative of the population from which it is drawn. So if we go back to the very beginning of this course, when we talked about the differences between descriptive and inferential statistics, and we said if there was something that we want to study that we can't have data on everything in the population of interest and we need to draw a sample, that's when we use inferential statistics. So here we know, how are we drawing those samples? How do we just come up with a sample? And to do something that's the higher quality type called a random sample, the first characteristic is that it has to be representative of the population. If we're going to use that sample to draw conclusions about the population, it has to be a sample that makes sense, that appropriately represents everyone in the population. Then the second characteristic of a random sample is something called the equal probability of selection method, or an Epsom sample. So in an Epsom sample, every element or case in the population must have an equal probability of selection for the sample. That means that everyone has the same chance of being picked for the sample. These are two different principles of probability samples, right? A probability or random sample has to have both of these, but representativeness does not necessarily mean Epsom, and Epsom does not necessarily mean representative. So this is the most straightforward technique for doing a probability sample, is called a simple random sample. So a simple random sample is a type of probability or random sample. And this is the most straightforward way to do it. And the steps in order to create a random sample are that you need to list all of the cases in the population with their own unique identifier. So this could be a number. And we need some system of selection that guarantees each case has an equal chance of being selected for the sample. And this is often done using something like a random number generator. In Excel, for example, has a random number generator, or online, if you can just Google random number generator and you put in a range of values like 1 to 10, and the computer spits out a random number, a randomly selected number for you. So if, for example, we wanted to study something like Philadelphians about their perceptions of the upcoming election. We would, in order to do a simple random sample, we would need a list of all Philadelphians. We would give each person a number, and then we would use a random number generator to pull out the numbers of people we would want to talk to. So if there are 1 million people who live in the city of Philadelphia, to do a simple random sample would be really difficult because we would need to list out all 1 million people, give each of them a number, and then use a simple and use a random number generator to identify which numbers for people we will select. So another example could be, and this helps to illustrate how simple random samples can follow an Epsom technique and yet still not be representative. So in addition to using a random number generator, another way to do it is if you have a number for everyone, you pick, like in this circumstance, they pick every third person, right? So you can start with like number 0 and you pick 0 is not counted. Then the third part, you start with 2, and then 3 people after that you select, 3 people after that you select, 3 people after that you select, in order to get your sample. So instead of using a random number generator, you can do something like selecting every second person or every third person in the list. What this illustrates, though, is if this is the population of different people and these using the Epsom technique, right, that this is an Epsom technique because everyone has an equal likelihood of being selected. It's not like, we're putting people who are in 1 through 5, we're only selecting them, right? We're just using something consistent like picking every third person or using a random number generator makes it an Epsom sample. But even when we do the Epsom techniques, we see here that this is not representative of the population. Why not? Is there one color of person that we just happen to miss in this? Yes, we're missing blue people in this pretend example, right? So this shows that even when a technique that you use the Epsom techniques, it's possible that it's not representative. And for it to be a good probability sample, it needs to be both representative of the population as well as following the Epsom technique. So this illustrates how Epsom does not guarantee representativeness. So what would we be doing in terms of like, what would a classwork or homework problem look like for the sampling questions? I might just say something, give you a pretend study or scenario, and you just need to describe the steps for me to get a probability sample. So perhaps the question is something like, we want to learn about the career plans for all sociology and criminal justice majors, but with 200 some majors, it's impossible for us to interview everyone. So we want to get a decent probability sample of sociology and criminal justice majors. How do we go about doing that? What steps would we use? And so in order to get the probability sample, that means we first need to list all 230 majors and assign a number to each, right? So each of the sociology and criminal justice majors is assigned a number, and then we use a random number generator. Let's say we know we want to just do 25 interviews. We use a random number generator 25 different times so that it spits out 25 numbers between 1 and 230, and then anyone with that number is selected for an interview. Alternatively, we could say we're going to pick just every 5th person. So the person who is assigned number 5 gets picked, the person who's assigned number 10 gets picked, 15 gets picked, etc. Right? These are the steps given for a probability sample, right? That you need to show that you're listing everyone out, giving a number to everyone, and then either using a random number generator or picking every 5th person, every 10th person, right? Whatever some level of systematic way of doing it you select could be. Okay, so that's considered a probability sample. So review, probability sample is representative of the population and is and follows an Epsom technique, the equal probability of selection. Everyone has a chance of being picked. The reverse of a probability sample is called a non-probability sample. This is anything that does not meet the Epsom criteria and is often referred to as a convenience sample. And so a convenience sample just means that people are not selected with some equal probability Epsom criteria, but rather are selected based off of the convenience of the researcher. The advantages of convenience samples are that they're more feasible or easier to do, but we know then that they tend to not be representative of the population. So we can't generalize results beyond the sample that we've looked at, beyond the group that's being tested. And so if we're continuing with like our example of wanting to interview sociology and criminal justice majors about their career plans, perhaps I just stood out. This is, if we were on campus, I just stood outside of my classroom at noon and snagged any sociology and criminal justice majors that happened to be walking by and said, "Hey, can I talk to you real quick about your career plans?" This would not be representative for a couple of reasons, right? Not everyone has an equal likelihood of being selected. I'm more likely to get students who are coming out of my statistics class and are juniors. So it's not all majors across all years. We're not getting evening students if I do that at noon, right? So that would be an example of a convenience sample because I'm just taking people who are closest to me, that are easiest or most convenient for me to sample, instead of doing the thing where you're listing out everyone has a chance of being selected. Okay, transitioning now to the second part of this lesson. So that's kind of like different types of samples that can be used. The second part of the lesson is on distributions and different types of distribution. So we've talked a little bit before about distribution is just an arrangement of values of a variable showing their frequency of occurrence. So think a distribution is when we look at a histogram or any of the normal curves. Those are distributions, right? We're showing how values of a given variable can be charted. And there's three types of distributions we can think about. One is called a population distribution. This is all values of a variable in the population, which is of course unknown, right? If we think about doing a question that's like, we want to know for sociology and criminal justice majors how many years it takes to graduate, right? This would be in our sample something that we would know. But if we wanted to say the values of a variable in the population of all sociology and criminal justice majors throughout the entire country, how many years it takes them to graduate, and our population of interest was sociology and criminal justice majors throughout the whole country, that would be something that's unknown, right? That we would have this kind of theoretical unknown population distribution. So the population distribution is just in whatever our population of interest is, how do the values on a given variable break down into a curve, into a histogram. Then the sampling distribution is something that's theoretical for all possible samples of a certain size. So also, this is also known as the distribution of a statistic or mean based on every conceivable combination of cases from the population. And as we'll look at, there's two rules or laws of probability that we will always know the shape, the central tendency, and the amount of dispersion, a standard deviation of a sampling distribution. So we'll see that in a minute. The sampling distribution is different than a sample distribution. This is if we take a given sample, how do the values of that variable draw out, right? How do we chart or graph those values on a given variable? The idea of a sampling distribution, though, is if we charted out multiple samples or an infinite number of samples, that would create a sampling distribution. And I know that kind of seems a little fuzzy now, but if we talk through some of the examples and illustrations, then these will make a little more sense. But try to get down at least just the given definitions for population, sampling distribution, and sample distribution first. Perhaps a helpful exercise could be to think about another example for each, that if perhaps we want to know what is the IQ of all LaSalle students. This would be probably unknowable, right? But we could draw a normal curve to show their IQs, like the IQ of all LaSalle students would be our population distribution. And perhaps though we take a sample of 100 LaSalle students and we know their IQs and we chart out their IQs, that would be our sample distribution if we took a sample of 100 LaSalle students. But if we took 30 different samples of 100 LaSalle students and charted out the mean IQs for each of those, that would generate our sampling distribution. So sampling distribution is essentially charting out multiple samples. Okay, so more on a sampling distributions. These can be created, and again, these are theoretical, that by taking an infinite number of repeated samples and recording the mean of a given variable for each of those samples. The example that's given in the reading is about, let's say we want to know the mean age of a community of 10,000 individuals, and it's impossible for us to question or get the age of all 10,000 of these. So we do multiple different Epsom samples. The first Epsom sample we take is of 100 people. And in this first sample, this has a mean age of 27. Then we do a second Epsom sample, right, with replacement of 100 other individuals. And this sample now has a mean age of 30. We do this over and over and over again, right? What we know about sampling distributions is that if the true mean age of the entire population was 30, the distribution of all of these sample means would peak at 30 and create a normal curve. So let's say we take this first, or we take one Epsom sample and the mean is 26. We could take a bunch of other Epsom samples and there's going to be more of them at 28, but the most of them are going to be around 30. And so the idea here is that a sampling distribution, if we take enough separate samples and chart those means, it's going to eventually represent what the true population looks like. And so that enough samples gets us to a sampling distribution that mirrors what the actual population looks like. Okay, so before we look at the two rules or laws related to this, and I think the laws are stated and in the text in a very dense, tricky way, but in many ways they are actually very simple once we look at some examples and how the distributions actually look. But just as a quick refresher here, right? X bar is the mean of the sample, mu is the mean of the population, S is the standard deviation of the sample, and this funky O thing is the sigma is the standard deviation of the population. Okay, so two rules or theorems is the term used in the reading. Theorem number one, and if you're taking notes, don't necessarily feel like you need to write down this whole thing because it's also in your reading. Theorem number one is for when the variable is normally distributed in the population. So there's the first theorem applies to when the population is a normal curve. And then theorem number two is what happens when the population is not a normal curve. What happens with the sampling distribution if the variable is normally distributed in the population? That's our first one. This theorem says that if we take repeated samples of size n of some unknown size from a normal population with this any mean and any standard deviation, then the sample distribution of sampling means, in other words, the sampling distribution will be normal with the same exact mean as the population and a standard deviation that's not the same as the population, but the same divided by the square root of n. No math that you're going to actually have to do for that. The big takeaway is that if we start with a variable that's normally distributed in a population and take an infinite number of random samples from that population, then the sampling distribution of those means will be normal. So, and the mean will be exactly the same as it is in the population. So let me give you an example. Let's say we want to study what is the average number of drinks that LaSalle students have on a Thursday night. And we know, again, this is like a thought exercise, and we know that the population distribution is normally distributed with a mean of 3, that the average number of drinks that LaSalle students have on a Thursday night is 3. There's some people who have absolutely none, there's some people who have a whole lot, but the average, the mean is 3, and that this is normally distributed. If though, and it's of course not feasible for us to interview every single LaSalle student about how many drinks they normally have on a Thursday night. So we could take a whole bunch of different samples, right? Some of these samples are going to have a mean of 1. If we sample 10 students and using an Epsom technique, the mean for those 10 might be 1. There might be a couple of Epsom samples then where the mean is 2, but the greatest number of samples are going to have a mean of 3. So the takeaway here for theorem 1 is just this is a rule of statistics that smarter statisticians than you and I have figured out over a long period of time, that if you take enough samples and chart the means for those samples, your sampling distribution is going to match what the actual population distribution is if the population distribution is normally distributed. Okay, so theorem number 1 just says if you have a variable that is normally distributed in the population, if you take enough samples to create a sampling distribution, the mean of that sampling distribution is going to match what the population distribution is. All right, theorem number 2, last thing here, theorem number 2 is called the central limit theorem. And this is when the population distribution is not normal in shape. What happens if we don't start from that normal curve, from a bell curve for the population? What happens then if we take a whole bunch of Epsom samples and create a sampling distribution? This one says that, and I will abbreviate or talk through all of this, statistical mumbo jumbo in the language. This one is saying that if we take enough random samples from any population, as the number of those samples becomes large, then the sampling distribution will actually approach normality, even if the variable is not normally distributed in a population. So let's say for our example with how many drinks LaSalle students have on average on a Thursday night, perhaps this in the population is not a normal distribution, but it actually has a real positive skew. There's more students that have very few drinks or 0 drinks on a Thursday night, and just some who have a whole lot, so that perhaps the population distribution is actually positively skewed and looks like this. What the central limit theorem finds, though, is that if we take enough different Epsom samples, no matter what the population distribution looks like, the sampling distribution will always be normal. And the why for this is way beyond the scope of what we cover in this class. But we can't be really explained well at this level. But that these are important statistical theorems to know, that even if the population distribution is not normal, if we take enough Epsom samples, the sampling distribution will look normal. And this is called the central limit theorem. In terms of how many samples need to be taken for the central limit theorem to apply, the general rule of thumb is around 100. So if we take 100 different samples of LaSalle students and how much they drink on average Thursday night, even if the population distribution is not normal, the sampling distribution will show up as normal. So there's huge implications of this for using samples to draw conclusions about a population, when we know, regardless of if the population distribution actually is normal or not, it's going to start to look normal if we take a large enough number of samples. Okay, so all of that will come into play more when we actually do inferential statistics for those of you who take 302, but this is all kind of laying the groundwork for understanding how and why things work. All right, so next up, work through the classwork for these 2 lessons. Check out the classwork answers. Send me questions if you have them, or let me know if you want to do a live class or do any of these together in a live Zoom. I would be happy to do that. All right, enjoy the day. Take care, folks.